Hello class, in this lesson we're going to learn about properties of tangents to circles. So here we have formal definitions for the interior and exterior of a circle. Think of the circle itself as a boundary between the two. And the interior is the collection of all the points that are inside the circle, whereas the exterior is the collection of all the points that are outside the circle. And here I have a diagram that shows a secant and a tangent. I'd like you to try to write your own definitions for these terms, and then I'll show you my formal definitions. So if you notice the secant, it's a line that intersects the circle 2 times, whereas the tangent intersects the circle exactly 1 time. And we call that point where it touches the circle the point of tangency. And there's a special type of segment called a tangent segment, and it is contained within a tangent, and one of the endpoints has to be the point of tangency of that tangent. So in this diagram, segment AB is a tangent segment because it's contained within a tangent, and B is a point of tangency here. So here's our first big theorem. We know that a line is tangent to a circle if and only if it is perpendicular to a radius of the circle at the endpoint where the radius meets that circle. So if this is a tangent, then we have to have a right angle over here at P. And the converse of this holds as well. If we have a line that's perpendicular to a radius at where that radius touches the circle, then that line has to be a tangent. So this holds in both directions. And here's another big theorem for today. We want to show that when we have tangent segments that share an endpoint on the exterior of the circle, that they are congruent. And to do that, we're going to go back to a triangle proof. So we have the outline of the proof here. We have some blanks in there that we're going to fill in. So let's see if we can solve this together. So they give us a construction to make. So we want to draw on these radii and segment AC. And we get this picture. So the goal is we want to show that these 2 triangles are congruent, because then we know that their corresponding parts are congruent. So what right angles do we have here? So we're given that these are tangent segments. So we know that these angles are right angles. So we have angle ADC and AEC. So if we have right angles, what type of triangles do we have? Right triangles. So how do we know that AD equals AE? Well, those are radii of the same circle, so they have to be congruent, so they have the same measure. And why is AC equal to itself? That's the reflexive property, right? So now we can say that the triangles are congruent because we have right triangles, we have a pair of congruent legs, and we have the hypotenuse congruent in both triangles. So this is a hypotenuse leg proof. And so now we know that CD equals CE because the corresponding parts are congruent. They have the same measure. And if we just substitute A and B in there, we get what we wanted. So here's some application. Given this diagram, how can we figure out the length of AC? Well, let's see. They give us the radius is 9 and that BC is 12. So let's make a right triangle using that information. So here's AB, which is 9. BC is 12, and so AC is hypotenuse here. So we can use Pythagorean theorem. Right? And then we evaluate this, take the square root, and we get AC is 15. So the answer will be 15 millimeters. So now we want to figure out the area of triangle ACD. Well, we just proved that these triangles are congruent. So it's the same as finding the area of this triangle, ABC. So we have a base of 12 and a height of 9. So 1/2 the base times the height gives us 54 square millimeters. And we could also just think of it as, all right, well, we have a 12 up here. And since these have the same endpoints, this one has to also be 12. They're congruent, right? And so if we want to figure out the perimeter here of quadrilateral ABCD, let's fill in our radii. We'll have 9 there. We'll have 9 down here. So we add up all 4 of those sides, and we end up with 42 millimeters. So how can we check if we have a segment tangent to a circle? Well, we know according to that previous theorem that if that's true, then we have to have a right angle here. To check if we have a right angle, we can use Pythagorean theorem. So we want to know 12 squared plus 35 squared, is that equal to 37 squared? And if we evaluate this, we get 1,369 for both quantities. So this satisfies Pythagorean theorem, so we have a right angle. So therefore, that segment has to be tangent to our circle. Now here's one that's a little bit trickier. We have a variable in there, but we're going to do it the exact same way as we did before. So we're going to figure out what the radius is, and they're telling us that we have a point of tangency. So AB is tangent here. It should have said AB is a tangent segment, but we're going to go ahead and assume that. So let's see, we have a leg of R, a leg of 80, and the hypotenuse is R plus 50. So if we plug all this information in correctly, we end up with this equation. All right, now we got to do some algebra here. Let's see, let's square this binomial. And let's evaluate 80 squared. If you notice, the r squareds cancel on both sides. Right? If you subtract r squared from both sides, those cancel. And if you subtract 2,500 from both sides, we get this equation. And to solve that, we divide by 100, and we get 39 feet. Now, if we return to our diagram from that proof in example 1, we also have congruent angles here. We know that angle DCA is congruent to angle BCA, because those are corresponding angles. So we have an angle bisector here, and this angle bisector contains the center of the circle. And so we have another theorem that says that we have a circle tangent to both rays of an angle, that when that happens, that the center has to be on the angle bisector. And remember, we can find the incenter of a triangle by drawing the angle bisectors and finding the point of concurrency. And in every triangle, we can find that incenter. And if you take the pivot on the compass and put it on the incenter, and put the pencil on the side, remember the shortest distance to that side, if you draw a circle, it's going to be tangent to the three sides. We can do that for any triangle. So let's apply some properties of inscribed circles. So let's see, we want to figure out how long segment DE is. And this isn't drawn to scale, so be careful. Well, DE is made up of two smaller segments, right? EG and GD. So if you can figure out how long those are, we just got to add them together. So let's see, this is 3 centimeters. And if the whole thing down here is 8, then this must be 5 centimeters. Okay, how does that help us? Well, since these are tangent segments, we know that they are congruent. So this one's 5 centimeters. So DG also has to be 5 centimeters. And similar train of thought here. If this is 3, then this one has to be 3. And whatever this one is, that has to be the same as this one over here. Okay, so let's see, this is 3. So this one's 3. This whole side is 7 centimeters. This one has to be 4 centimeters, right? 7 minus 3 is 4. So this one is also 4. So we end up with 4 plus 5, which gives us 9 centimeters for our answer. In this lesson, we learned about the properties of tangents to circles. Thank you for watching this video.